So today's an interesting day. We're going to talk about local bond theory, and it's what you've been working with, essentially since freshman chemistry. And we've used it in this course extensively. When you make the Vesper shapes, you're using local bond theory. You make the Lewis dot structure, and you do the Vesper shapes and so on. But we're going to see today that maybe that theory is not universal. Okay, so we're going to dive into local bond theory, know it really well, but then we're going to show some issues with it. Okay, so let's dive in. So local bond theory is essentially the theory that you've grown up with. Okay, it's how you know about bonding. Let me just make sure the recording is going. Yes. And so let's just state it explicitly so that you know what we're talking about when we talk about local bond theory. So what is the local part of local bond theory? It's the fact that there are two electrons located in that bond. So like between the oxygen and the hydrogen, local bond theory tells you there's two electrons between those two nuclei, and that's what holds them together. Okay, sounds familiar, yes? And so that's the local part when we say local bond theory. Also the lone pairs, where we draw them, that's where those two electrons are. Okay, so this I see people nodding, that's good. And this also is the acknowledgement that the 8-electron noble gas configuration is unusually stable. Remember the first ionization energy, we just talked about that. There seems to be some stabilization for the noble gases, and those have 8 electrons. They have 2 electrons in the s orbital and 6 in the p orbitals in the subshells. And so then that seems to be a stable configuration. And so local bond theory works things out so that we have 8 electrons nearby each atom. Okay, and so that's called the octet rule, and it's strongly adhered to by carbon, nitrogen, oxygen, and fluorine. But really, carbon, nitrogen, and oxygen. We will form double bonds in order to give that central carbon or oxygen or nitrogen 8 electrons. It's very familiar to you for making things like CO2 and so on. And so this requires or drives the Lewis dot structures. So just to refresh your memory, this is how we do the Lewis dot structure in stepwise formation. We sum up the valence electrons for all the atoms that are shown. We create a single bonded framework. Typically there's a central atom for all the ones that we give you. Like if we say PCl5, you have phosphorus and 5 chlorines. You sum up all the valence electrons, you put phosphorus in the middle, and you make a sigma bond for all of the chlorines around the phosphorus. And then you subtract 2 electrons from that total for each of the single bonds. And then you place non-bonded pairs on the most electronegative atoms. So if this was PCl5, those chlorines are more electronegative. And so you put the non-bonded electrons on those chlorines and subtract those from the total. And if you have any left, you put them on the central atom. But a lot of times you run out when you put them on those outside atoms. So this should be very familiar with you. And then if you have carbon, nitrogen, oxygen, or fluorine, but most of the time it's just carbon, nitrogen, and oxygen, you form double bonds to make sure that those atoms have an octet. And so then we would use the Vesper shapes, that valence shell electron pair repulsion, because we've done all of these bonds with electron pairs, and so that's where the electron pair comes from. And so the repulsion of those electron pairs is what gives us our 3D shape. And that's what makes methane go from a planar structure, carbon with 4 hydrogens around it, to a tetrahedral structure, because you want to get those electron pairs in those CH bonds as far away as possible. And a tetrahedral shape has 109 degree angles, whereas a flat planar shape would only have 90 degree angles. So it does get them quite a bit away from each other compared to 90 degrees. So let's practice a little bit, and I'm going to add a couple of things to this practice that you haven't done before. Okay, so let's do the Lewis dot structure for water. So up here we have water. What's the total number of valence electrons? All right, so we have 6 for the oxygen. You count over there, 6, and then 7, 8. 1 each for the hydrogen, so we have 8 electrons. So then we draw the oxygen here. I'm going to draw it linear first. Okay, just like a freshman would do it. Okay, I formed my sigma bonding network Okay, so I've got sigma bonds everywhere. I've used 2 electrons for each of those bonds, so that's 4 minus 4 bonding electrons. And so now I have 4 non-bonding electrons. Oh wait, okay. So I put 1 here, or 4 on the oxygen. It's more electronegative than the hydrogen. So then I subtract those from the total. So minus 4 non-bonding electrons, NBE, and I have 0. So this is big review. Then we use the VSEPR theory, which is the valence shell electron pair repulsion theory, to look and count the electron domains around all the different atoms. In this case, we look at oxygen. It has 4 domains. That means it's going to be tetrahedral electronic structure. Okay, listen carefully to my words. This is the electronic structure that's tetrahedral, not the molecule. Okay, so then we're going to draw that oxygen with a bent molecular structure. And these non-bonded electrons are actually in front and behind, but we just draw them on there. So this is the tetrahedral structure. That gives us tetrahedral electronic structure, bent molecular structure. It's roughly 109.5 degrees. That's a initial guess at that angle. But it predicts that this molecule would be bent. Okay, so local bond theory, the VSEPR shapes predicts that this molecule would be bent. Let's do CO2 now. Okay, so we have 6 for each of the oxygens, so that's 12, and then another 4, 13, 14, 15, 16 electrons. 16 valence electrons. Let's build the sigma framework. Carbon, oxygen, oxygen. So 4 electrons bonded. So I have 12 left over, and the more electronegative element. Now when I talk about electronegativity, that's really dating back to your freshman chemistry. We haven't explained that, but really electronegativity increases towards fluorine. So fluorine being the most electronegative element. So oxygen's closer to fluorine than carbon, and so we'll put those non-bonded electrons onto the oxygen to make an 8 electrons per oxygen. So we used up all 12. Then we evaluate this. Over here, let's go back to water and we look at this. In determining how many electrons that an atom can claim, it claims everything it's bonded to, so 2 electrons for each of the bonds, and then all of the non-bonded electrons. So that oxygen has 8 electrons around it. And when we talk about covalent, think about that. Those electrons in the bond are in the valences of both atoms. So that's the word covalent. Both atoms can count those electrons. So looking at this carbon, it's only got 4 electrons and it wants 8. And so it's going to drag 2 electrons towards itself. I should have drawn that to the bond. Let's do that here. And so we're going to form double bonds on either side of the carbon. So now the carbon has 4 bonds around it, 2 electrons each, so it has 8. And the oxygen didn't lose any electrons, it just shared more. And so it also has 8 electrons. So the octet rule for carbon, nitrogen, and oxygen, that's satisfied. Okay. And now we look at the VSEPR shapes, and the carbon in the middle has 2 electron domains. And so there'd be 180 degrees apart. So that's a linear electronic structure, and it happens to be a linear molecular structure. So in that case, they both match. me go ahead and write those on here. So this is linear So linear electronic structure and linear molecular structure. Whereas this water here is tetrahedral around that oxygen, but a bent molecular structure. Does that help you to distinguish between those two? The electronic structure is around a particular atom, but the molecular structure is for the whole molecule. Yes?
So would oxygen, in this case, have a trigonal planar electronic structure?
No, but it could. I mean, if we could write it either way. We could say that two of those lone pairs are in an unused pz orbital, and that we would have these hybrid orbitals. So I would look at that and say 4 electron domains, it's sp3, so it's tetrahedral electronic structure. Trigonal planar would be sp2 hybridized.
No, I mean oxygen on the...
Oh, over here, yes. So these oxygens over here definitely have 3 electron domains, and so those would be sp2 hybridized, trigonal planar. And so this, let's do that. So notice how these have 1 here. An electron domain takes up, these different pairs, and so that's got 3 domains around it, so that'd be trigonal planar. So that'd be sp2 hybridized. And then this oxygen over here would be sp3. So that's all review. What I'd like for you to think about now is if we pulled electrons out of these 2 molecules, how many energies would we have? So if I reached in and grabbed this electron, I would have to overcome the binding energy to get it out, right? And how many types of electrons are in each of these molecules? Because if it's a different type, it'll have a different binding energy. But if it's the same type of electron, it'll have the same binding energy. So if I look at this molecule and I see an OH bond, both of those OH bonds are the same, right? Even by symmetry, you can rotate them into each other. So they would be the same. And so they would have a particular binding energy. If I'm pulling out an OH bonding electron, I'll have an energy associated with it. If I'm pulling off a non-bonded electron, it'll have a different energy. But I've got 2 lone pairs that are the same, and so those will all have the same binding energy. So how many different types of electrons do I have in this molecule? 2 types. Two types of electrons, and that equals 2 binding energies. And then for CO2, how many types of electrons do I have?
3.
Yeah, it's the non-bonded ones, it's the sigma bonds, and the pi bonds. So the sigma and pi bonds are different kinds of electrons, and so I would have 3 types of electrons in the CO2. So this is the new part, and this will allow us to evaluate if this theory is correct. 3 types of electrons. The dots, the sigma, and the pi. Does that make sense? I'm running out of space, but I have the non-bonded pair, the sigma bonds, and the pi electrons. 3 types. So if I were to stick CO2 in a beam of UV light and blast those electrons off, I should see 3 different peaks for the 3 different types of electrons. Or water, if I put water in a UV light and I could knock those electrons off, I should see 2 types of electrons emerge. In fact, that's what we have in terms of experimentation. But before we get there, let's think about what we've got so far. We've used the Lewis dot structure for all of our structures for point groups and so on. And so we realized that water is predicted to be bent by this very simple theory. So local bond theory and valence shell electron pair repulsion tells us water is bent and CO2 is linear. Okay, and our experimental data confirm that. You know, this is not just the vibrational spectra, which takes into account different bonds, and it even tells us that double bonds are stronger than single bonds because we've got two springs holding these atoms together. So it matches vibrational data and it matches rotational data. Rotational data, CO2 is a symmetric top, and so it has a beautiful P and R branch, whereas water is an asymmetric top. So instead of the rotational constant B, it has A, B, and C. So it has three rotational constants because it has three different rotational axes and they have different moments of inertia. And so you have P and R branches on top of P and R branches. So you have three different rotational spectra on top of each other, and that's why water looks like a mess. So these are the rotational bands for water here and here. And you see it's very difficult to understand those two spectra because we have three overlapping P and R branches. And then here we have CO2 and CO2, and this is beautiful. You know, here we have the P and the Q and the R branch right there, because that's the perpendicular band, and here's the parallel band, and you have the P and R branch here and there. So local bond theory has given us good structures. It's given us good rotational constants. It's helped us understand, you know, this spectra up to this point. But then we go into an electronic experiment like X-ray or UV photoelectron spectroscopy, and we run into some trouble. So here we have the X-ray or UV photoelectron spectrometry experiment where you have either X-ray or UV light coming down and hitting your sample and ejecting photoelectrons. So light comes in, that's the photo part, and electrons come out, that's the electron part. And they come out with different kinetic energy. And you can kind of think of it as they lose the amount of energy it took to get them out of the molecule, and then they have excess energy that adds up to the photon of light that you hit it with. So energy is conserved. And so you measure this kinetic energy just like you would measure the kinetic energy of a car turning on a turn. You know, the mass and the velocity are going to allow that car to turn a certain radius. So we have the mass and velocity of the electron allowing it to turn as a function of electric field because it's negatively charged. So we have this energy analyzer that analyzes the speed or kinetic energy of that electron as it comes out of the molecule. So it's a pretty simple experiment. Hit it with light and measure the speed of the electrons that come out. And so if we put water into this experiment, we should get a photoelectron count versus binding energy. And so we scan this analyzer and we say, we don't see any electrons with this low binding energy, but then all of a sudden we see some electrons at this binding energy, and then we see them at that binding energy. So we measure the kinetic energy spectrum of the electrons that come out of this. Now, what's the deal with X-ray and UV? X-ray will get you down to the core electrons, like 1s electrons. And UV photoelectron spectroscopy, or UVPS, will get you the valence band, and that will tell you about the bonding. And since we're evaluating local bond theory, this is what we want to do. So UVPS, although sometimes I slip and just call it broadly XPS, which stands for X-ray photoelectron spectroscopy. If you're looking in the valence band or the bonding, you're really using the UV light. Okay, so don't be confused. I sometimes slip and use those interchangeably. So this UVPS spectrum of water, if local bond theory were true, would have lone pair electrons and the OH bonding electrons. And so we should see two peaks. Okay, so what I require of you is if you draw the Lewis dot structure of a molecule, any molecule, you should be able to tell me how many peaks would be in the UVPS spectrum. And so when I'm talking about two different types of electrons, that would be two peaks in the UV photoelectron spectrum. And so let's take a Kahoot and practice that. So we'll look at a bunch of different molecules and see if you can predict how many photoelectrons would be in the UVPS spectrum.
So is that the hydrogen when it's broken off and the OH left behind?
Mm-mm. It's the electrons that are holding the hydrogen and oxygen together. Okay, so it's UV light's coming in and pulling electrons out of that bond. And so both of those electrons are the same, and both OH bonds are the same. And so there should be 4 electrons that could come out of both of those bonds. And they would all have the same binding energy. And then the lone pairs are different. And so even though these peaks have different shape, I tried to make this one taller and skinnier and that one wider and shorter. So they have the same area because they have the same number of electrons. Okay, so, all right, so let's take this Kahoot. Okay. Yeah, I don't know why it's doing this to me. Oh, it's up over here. Oh. Why is it doing that? Hello. All right. The code is 812-7814. 8127814. Spooky music. $45 people. Is that everybody? Okay. 46. Was that you, Tracy? Still not? Okay. All right, we're good. Thank you. All right, so again, this is just counting up those different types of electrons. How many valence band UVPS peaks does the local bond theory predict for this molecule? So I've drawn all the little hybrid orbitals, so just count up the different types of electrons. Started you with a hard one. Yeah, so 3. So we can look at that molecule and we can see the different types. We have the sigma bond between the 2 carbons, carbon-hydrogen single bonds. All 4 of those count as one type of electron, and then the pi electrons. Okay. Oh, I just told you. This one, so get your thumbs ready. So what are the 3 valence band UVPS peaks predicted by local bond theory? Yeah, so the sigma CH is one type, sigma CC and pi CC.
All the other has sigma HH.
Yeah, I know. This HH, hydrogen bonded to hydrogen. No, not in this one. So how many valence band UVPS peaks would CO2 have? One more. Yep, 3. So it's, which ones are they?
The valence electrons and the double bond.
Yeah, sigma pi and the non-bonds. Yeah, non-bonds. Yeah, excellent. Okay. Now this is if the oxygen's sp3, how would it be? So 2, 3, 4, or 5. So water. Okay, very good. 2, we got the bonded electrons and the non-bonded electrons. Now, when I did this calculation, you can force Gaussian to use Vesper theory. Okay, I don't know why. I think it's the organic chemists messing with it. Okay, they shouldn't do that because it's totally, well, I can't give it away, but it's not right. Okay, and if you force Vesper theory on Gaussian, it will actually calculate that oxygen as sp2. So that's why when you asked about sp2, you were talking about CO2, and I thought about water because I go there in the next 1 or 2 lectures, and so Gaussian calculates that oxygen as sp2. Okay, and so if that were the case, like who knows? Maybe nature is that way, right? If oxygen were sp2 in water, how many electrons different types of electrons would it have? So think carefully. Force that oxygen to be sp2 hybridized. Okay, very good. So you would force one of those lone pairs in an sp hybrid, and the other lone pair would be in the pz orbital that's unused. Okay, we call it pz because typically a trigonal planar structure would have the z-axis out the top. And so if that confused the heck out of you, don't worry about it. Just oxygen's sp3. How do we know oxygen's sp3 even without using electronic spectroscopy? 2 hydrogen bonds, yeah. And so the hydrogen bond angles in ice would tell us that it's sp2 hybrid, meaning it can form 2 hydrogen bonds. Okay, very good. Very good. I'll get those results later. Now let's go back to our lecture. So this was our prediction if local bond theory was true. Okay, we took the Kahoot. Molecular orbital theory is the contrasting theory to local bond theory. And think about what the words mean. Local bond theory means the electrons, 2 each, are local to the bond. Okay, molecular orbital theory, it's all in the name. It's a molecular orbital. The electron is not associated with a particular bond. It goes over the whole molecule. And we're going to generate this chart later when we really get into MO theory. We've shown it a couple of times. But let's just think about this. We've got the atomic orbitals on oxygen, the atomic orbitals on hydrogen. We give them a certain symmetry. Now, this is a little strange in that we use local bond theory to come up with the shape of the molecule and the point group. And then we take that point group and do molecular orbital theory with it. So we start with local bond theory, and then we build the molecular orbitals using molecular orbital theory on top of that framework. And so then you get these orbitals in the middle. Notice that these 2 electrons are not associated with any particular bond, and they're not associated with sort of a non-bonding thing on the oxygen. So which bond do these 2 electrons go to? That's almost an invalid question, right? Because that's local bond theory when you're thinking about 2 electrons contributing to a bond. So this is molecular orbital theory, so that question is really invalid. Which bond do these 2 electrons go to? And so this is a molecular orbital, that's a molecular orbital. Now you can still look at this and say that this orbital contributes something to the OH bond because you've got these positive nuclei and there's electron density around and between those positive charges. And you look at this one, and this has a node in the middle. So this particular molecular orbital does not really contribute to the bonding between the oxygen and the hydrogens. We might say that's non or anti-bonding because there's a node that breaks those bonds. Here, this one contributes to the bonding between the oxygen and the hydrogen because the node is right down the middle of the oxygen, but there's electron density between those charges on the nuclei on either side. Remember, if we squared this wave function, that would be the position of the electrons. So that would be the location of those electrons. By squaring it, you just make it all one color. Okay, and that would be where the electrons are. But now you see the molecular orbitals. Now, how many peaks are predicted by molecular orbital theory in the X-ray or UV photoelectron spectrum? Well, down at the bottom, you have an oxygen 1s, and that would be in the X-ray region. And then you get into the UV, where you're looking at the bonded. And we label them by symmetry. So A1, that would be an A1 orbital, the 1s orbital on oxygen. And then the 2s orbital interacting with the 1s is on the hydrogen. The lowest energy one would be this, so and that would be the second A1 orbital. And so that would be a peak. And the third A1 orbital here, and then a B2 orbital and a B1 orbital. And that's all the ones that have electrons in it. And so we would have 5 peaks predicted by molecular orbital theory and 2 peaks predicted by local bond theory. This is great because they're different predictions. Then we go to experiment and see which one matches. You see what we're doing? So we have predicted 2 peaks for local bond theory, 5 peaks for UVPS and XPS. And then we go to the experiment and we see these peaks here for the valence region, and then actually Gaussian has these two switched, the A1 and the B2, but they're still both there. And then the 1A1 and the 2A1 are at higher EV. But we definitely see more than 2 peaks, right? In fact, molecular orbital theory matches the experiment, where we send light in and we pull the electrons out. So this tells us, in terms of the electron cloud, we really need to use molecular orbital theory. Okay. And here's just evidence that local bond theory is lacking, and this is in the notes. You can kind of read a little bit about the paper. So this leads us to kind of a problem. Do we throw local bond theory out totally or not? And so this is now a sort of an aside, because this is a great time in your scientific career. Okay, right now you're learning about 2 different theories, and they both have merit. So what do you do in that situation? How do you evaluate theories? This is now philosophy of science, but it's really about philosophy of knowledge. How do you evaluate 2 competing theories? There's one way, yes. And so what do we call matching the experiment? So explanatory power is one criterion for evaluating a theory, okay? And what does that mean? It has the ability to match the data in the training set. So that's your experiment part, right? You have all these experimental data, and we would call that the training set. Training set for what? Well, you're developing a theory, right? And you're going to train against this data, and you're going to refine that theory against that data. And then you're going to apply it to data that you haven't taken yet. So that'd be the predictive nature. But the data you already have that you use to develop the theory, I call the training set, right? It's the known data that you use to develop the theory. Okay. And then explanatory scope. So how large is the training set? How much data do you have? If you just have 3 experiments, and like in this situation, we just have water. I've just shown you 2 spectra of water, but this goes on and works for dozens and dozens, or I don't know, many, many more molecules. So how large is the data set? And then how diverse is it? Is it just X-ray data, or is it also infrared data or rotational data, right? So how diverse? That would be this explanatory scope. So what's the scope that this theory covers? And how big is the data set in that huge scope? And then how well it matches is the power of a theory. And then this is a new term for you probably. Ad hoc is Latin for this. Okay, so ad hocness. And you don't want a lot of ad hoc adjustments to your theory. So if your theory has lots of exceptions or special cases, like it applies in this case, but not that one and not that one, so we have to tack on a few things. If pretty soon, if you have all of these exceptions, your theory is pretty weak, right? So you want a very few amount of exceptions in your theory. So these are 3 criterion for evaluating theories. And now these 3 criterion are not just used in science. They're used in history, philosophy, sociology. Every discipline that has a theory is thinking about these 3 things at least. There may be others. but they're looking at how well does it describe the data, that's power. How much data can it describe, and what's the diversity of that data, that would be the scope. And then how many exceptions does it have? So let's look at local bond theory. The explanatory power is big, okay? It accurately measures or predicts with the Vesper shapes molecular structures. Now I say accurate, the water HOH bond is probably not 109.5, okay? But it gives you a very good initial guess. I mean, if you can take local bond theory and start with building things like water and CO2, and then use the same theory to build DNA, the double helix, that's a pretty good theory, right? And it can get all of those bonds straightened up. And that sort of tells you about the scope as well. It matches the rotational spectra. It predicts bent and linear molecules and other kinds of shapes. And then it matches the vibrational spectra too, for the double bonds and single bonds and things in the molecules that would give you different fingerprint region peaks. But it does not match the electronic spectroscopy. So there's a big hole there in this theory. And it does have some ad hoc nature to it. This whole business about the octet rule for really being strongly adhered to for carbon, nitrogen, and oxygen, but being relaxed for phosphorus and sulfur, where they can have sulfur hexafluoride, but not oxygen hexafluoride. Right? Have you ever thought of that? Oxygen has 6 valence electrons, but you can't put 6 fluorines on it. Why not? You can for sulfur. Okay, and so you've got some special cases in the local bond theory, and that raises its ad hocness and weakens the theory. So then let's look at molecular orbital theory. Of course, it also accurately models molecular structures. It has a huge explanatory scope. It matches rotational spectra and vibrational spectra. It returns those same structures, even a little better if you have a computer that you can use it on. And then it also matches the electronic spectra. So the different numbers of orbitals that we get from molecular orbital theory, if we go to electronic spectroscopy and hit it with light and pull those electrons out, we accurately predict the binding energies for those electrons. And there's really very little ad hocness to the molecular orbital theory. We don't have any special exceptions. It works for hydrogen, H2, all the way up to, like I said, DNA and things of that sort. So how do we choose between theories? Do we use molecular orbital theory for everything? Yeah, if you have a computer, right? But even then, with Gaussian, what are you going to do? You're going to use local bond theory to build your molecule, aren't you? Okay, and so local bond theory is easy, and molecular orbital theory is not that easy. Okay, but for molecular structures and for rotation and vibration, sort of predicting this is a double bond, that's a single bond, this is kind of half because of a resonance structure, you can get pretty far down the road for understanding vibrational spectroscopy just with a pencil and paper. And so if you can use a pencil and paper for a theory, go with it, as long as that's within the scope of that theory. And that's the words I want you to think about today. If it's within the scope of that theory, and that's the easiest route, you can use it. But if it's not within the scope of that theory, don't try to force that theory to do something that it can't do. And so for electronic spectra and bonding, we need to go to molecular orbital theory. So actually understanding, how the bonds are, where those free electrons are. Like I said, when we talked about nucleophilic attack or electrophilic attack, looking at the electrostatic potential, that all requires molecular orbital theory. You can't get there from local bond theory. Although, and I was joking, but although the organic chemists try. You probably in organic chemistry were looking at a lot of sp hybrids and non-bonded things of that sort to try to explain the organic chemistry of bonding and so on. And that's just really forcing local bond theory to do stuff it wasn't meant to do. When we started using Gaussian to explain organic chemical reactions, it got better. Okay, but it's hard to force that down into the sophomore year. So when you go into organic chemistry, you're going to start then doing more Gaussian calculations to explain how reactions will split and give you this much yield of that kind of compound and that kind of compound. Okay. And so that's really it for today. Just wanting to drive home, not just that as we move into molecular orbital theory, we need it for electronic structures, but also how to evaluate different theories. And so hopefully I've given you some good tools for the future. Thanks.